Okay, thank you, and thank you, James and Ankit, for giving me the opportunity to talk. I will try to continue with what Daniele has presented before, and I want to give it a little bit of a different flavor. I will give you, hopefully, an idea of how we can frame a theory that is able to describe these quantum effects in cavity materials engineering, and then I will show you few examples of motivating what you can get and what are the properties you can see without getting too much into the details, but I'm happy to share with you all the details afterwards. Okay, I wanted to phrase this thing of cavity materials engineering in two aspects, because I think it's a little bit of a problem in the community. One thing is that you have a dark cavity, another thing you have the pump cavity. The pump cavity is the one that Daniele was presented before, and let me make the case that at temperature, the way you can see it is pumping. You are putting photons in the field. Then we have to be careful how we address those things. Then in this case, when you have this cavity in the material, you have something which was discussed before, which is these exciton polaritons, vibropolaritons, and all that, which is the interaction of any excitation in your system with the photon field. No? And those is something that Daniele was discussing. This RUBIO splitting is very small if you consider single molecule. However, that RUBIO splitting scales as a square root of n with the number of emitters in your sample. However, there is a misunderstanding connecting this huge RUBIO splitting with having a strong light-matter coupling. There is nothing to do between the two. You get a huge RUBIO splitting in linear response theory. And it's not a question of a strong light-matter coupling. Then we have to be careful with that because this is important. And then I wanted to tell you that everything that we've been discussing so far is, the previous talk is vibropolaritons, which is coupling to vibrations. Exciton polaritons is something that is interesting, was mentioned plasmon polaritons. But what we did with Dimitri is look for the last 60 years how many polaritons are there. And there, at least up to last year, there were 70 types of those. Then you can mix every type of bosonic excitation in your system, you dress it with another photon field, and then you do combinations of those. And then you can do a zoology of combinations. Then you can have photon, excitons, and phonons, which is called phonoriton. And this was that name, although we thought with NuGet that we were original, was proposed by Keldis 30 years before us. Then there are many of those combinations that give you the zoology of things that you could eventually condense and address to motivate new materials phenomena. What are you going to use as the ingredient to get new quantum materials? This is the whole idea, no? But the question that I want to go back is whether we can really modify the materials phenomena by the coupling to the quantum fluctuations. Okay? This is the whole setup. Daniele has presented one case in which the conclusion is you do, but the reason why you do is because of the temperature, not because of the modification of the electronic structure. And the question is, under which conditions you could get something else, no? And then something which is important, and I think this has not been addressed so far, and I will not do it, but I am happy, is that cavities, forget about cavities, electromagnetic environments, metamaterials are a wonderful way to break symmetries in your system. You can have a perfect time reversal symmetric system with inversion symmetry, and you can create an electromagnetic environment that breaks inversion symmetry and time reversal symmetry. And then all the phenomena that is connected to topology will pop up immediately just because you have engineered the quantum environment. Okay? This is one case, is chiral cavities that will make, for example, graphene being semi-metallic to have a gap. Okay? Just by breaking time reversal symmetry. And then the thing I'm not going to discuss, as neither Daniele did, is the modification of chemical landscapes, but I'm happy to discuss it in detail if you want. Okay? Then let me just give you a flavor of what has been discussed of the cavities. This was more on the summary. You have the normal Fabry-Perot cavities, which is you have the linear polarization, which you generate, and then you have an infinite degree of modes, which are in plane, and then the dispersion out of plane, and then the standard confine of modes that you have. By just having helical mirrors, you can have helical modes. Don't forget that those helical modes do not break time reversal symmetry because they are symmetric, but those are easy to generate with standard mirrors. Then you can have Faraday modes in which you can separate left-handed and right-handed modes in different regions of space, and this enables the having regions in which you break time reversal symmetry if your material is thinner than the wavelength of the mode that you are studying, and toroidal modes. Okay? Then basically here the only thing I was showing to you is what you can get from metamaterials as a way to engineer the quantum electromagnetic environment to break symmetries. Okay, this is one thing. The other aspect is why we want to do it. And then first thing is this cavity quinty in solids, which you have this input-output theory that was described to analyze the properties of the material in the cavity. And the first thing you do is just takes you 1 minute to look what is the 0-point energy and the spectral density of your system. And then if you plug numbers, you eventually realize that those effects are tiny. What I think is important that it's tiny but non-zero, in spite of the fact some people claiming it's zero. And those effects, you can call it the Lamb shift, which is the shift of the total energy of the system, van der Waals forces, or the Casimir forces. Or if you want, also how gravitational waves were measured were also raised with cavity mirrors that were moved with 10 to the minus 20. Then this effect is there. It's a question of how you enhance it. Okay? And now is where it comes the solid. In the solid, you have many emitters, which is what was discussed before. You can have large dipole moments or large spins, and then you have many electrons, and then you have all the ingredients to benefit from this ultra-strong coupling due to the square root of n that I was telling you before. It was not giving you the ultra-strong light matter coupling, but you can benefit from that. And then the question is whether those hybridized states do indeed change the electronic properties of a material. Okay, let me make a digression that I think is important. If you believe that when you come with light, you get excited states that are different to the ones that you have without light, because you have this RUBIO splitting, you just only need to do an inverse orthogonalization procedure to conclude that the ground state has to change, because otherwise it cannot be orthogonal to the excited states. Then basically there is, and there has to be a change of the ground state. The question is how important it is. Okay? Then that's something that I wanted to address, and then let me spend a few minutes on what is the framework. The framework, you can take the standard framework of quantum electrodynamics, in which you have your electronic structure, and then you have your focus space for your photons, and then you combine it, and then you immediately realize that this blows up exponentially, and it's something that you cannot do. And the question is, can we set up something which is similar to what we did 50 years ago with DFT? You take the many-body problem and you map it into a problem which is easy to solve, which is in terms of the density, but you don't have the exact functional. Then it's a question of solving approximately the exact Hamiltonian or solving exactly an approximated Hamiltonian. The question is, can I do the same in the case of having electrons interacting with photons? And if you solve it that way, you can do it for electrons interacting with photons, with bosons, with magnons, with any bosonic excitation. Eh? Then just that's the whole idea. And the setup is easy because the only thing you have to do is you go to the standard non-relativistic QED, in which interaction between particles is mediated by photons, and then it's a nice way of having both the interacting particles with photons and the external photons treated equally. Then in that setup, it's easy to set up this QED DFT theorem that I will not prove it to you, but what I want you is that you take home that as in DFT, the full many-body of the interacting system is determined just by knowing the current of your system, which were the current fluctuations that Daniele was mentioning before, and the photon distribution, or the electromagnetic distribution of your system. You only need two quantities, which are, this is really a simplification. The only thing is that you don't know the functional, okay? But this is a big thing, because then you have a one-to-one correspondence, and this is exact. And if you just plug it, eventually this end up in having to solve a set of n-independent Schrödinger equations coupled to n-independent Maxwell equations for the photon field. Okay, then you might ask, okay, so far so good, but can I do something else? Because this is a proof of principle, then there is no functional. And then I want to show you how you can get the lowest level functional for electron-photon interacting system that is going back to the LDA in the 50s. But this is what gave rise to the Nobel Prize in DFT afterwards. Then maybe eventually you can get better functionals. Okay, then I write you the Hamiltonian of the full interacting system, that you have the electronic part with the Coulomb interaction, the coupling to the photon field on the transverse, and then all the photon modes. The first thing you want to do is, this is the part you don't want to treat, because this makes the Hilbert space growing exponentially. Then the first approximation you might think is, if you take classical electrodynamics, what do you think? It's just you have an electron moving, and this current that the electron is generating is the one that is the source of the electromagnetic field. This is called one of the normal approximations, and then what we are going to describe is the fluctuations of the electromagnetic field are proportional to the current in the matter. This is an approximation, okay? That is being used in relativistic theory to reduce the expansion only to the first order in relativity, which, if you just do that assumption, tells you that this creation and nucleation operator of the photon field can be written in terms of the matter. Then you just close the equations. Then all of a sudden you end up in a problem in which the only thing that appear is matter operators. And this is the time-independent effective photon-free Hamiltonian that we are going to use from now on the rest of the presentation. There you have the electron-electron interaction that I just kept the Coulomb part, because here is the transverse part included, and then the photon fields are just included by discretization of the cavity modes, which are renormalized, plus this interaction with the currents in the matter part. Okay, this is the whole. In the language of people that knows relativistic theory, if you go to, it's what they call the bright approximation in relativistic theory. This is equivalent to what we are doing. That we know the bright approximation is not good for atomic physics. However, this type of approximation, we solved it for the homogeneous electron gas, and for different cases is extremely good for the extended systems. Okay, then basically just to, and then I will, if you want details, I'm happy to discuss. Then at the end of the day, what we have is a interacting problem in which you have the kinetic energy of the electrons, the external, which is the electron ion potential, the Hartree change and correlation potential. That is an open problem because we have to get approximation. We are not solving the many-body problem as was solved before, but then you get the best approximation here. You can put coupled cluster if you wish. And then this photon exchange potential and the photon correlation potential that is based on the LDA for the photon electron, homogeneous electron gas. Just to give you the expression, it's analytic. You can get the one for the LDA of the photon field, which is just product of correlation, which is the current fluctuations that Daniele was discussing, but this is a way to put it in words how it looks like in practice. And if you plug that and then you solve a ring of two electrons interacting with two photons, this gives you the exact solution. Then this is exact for one electron, one photon mode, for two electrons, one photon mode, and for infinite electrons and one photon mode. Then it has all those limits exact. Okay, tell that, and in between we assume is good. Okay, then this was one thing, and the second thing that everybody criticized, but I'm going to show you and then go a step back. I will present all the results in the Fabry-Perot cavity. But in the Fabry-Perot cavity, you put by hand the light-matter coupling. You might ask, can I get the light-matter coupling ab initio? The answer is yes. The only thing I need to do is the input-output theory, in which I have a cavity. In this case, I show you a spherical cavity because it's analytic. Then we can do it analytically, in which you come with the coming photon in, photon out, and then you do the interaction with a molecule or a solid in here, and then you can get, depending on the size of the cavity, the Purcell effect and the light-matter coupling automatically. The way we do it is with the QED DFT theory inside plus macroscopic QED outside, which macroscopic QED, if you put it in your language, is nothing less than metamaterials, the one that people is using with classical electrodynamics. And this is nice because you can get both the strength and the width of all the modes in your cavity, and there is no external parameter. That's good, and then this can give you, under which conditions you get strong light-matter coupling, which here you see the narrower the cavity, the bigger the coupling, although you get larger line widths, as Daniele was discussing. Okay, then this was to give you the flavor of what is the theory, and then let's take that theory and remove the cavity. Then for now on.
Sorry for interrupting. Gives rise to one? Is it the interaction with the...
No, basically what you are putting is, for the sphere, you are defining that as a dielectric media in which you have permittivity and magnetic susceptibility that has a frequency dependent, and then this gives you an imaginary part. Then basically this tells you that your mirror has a probability of light coming in, reflected, transmitted, and this is.
Then you do not have a Hamiltonian description.
No.
Of the cavity.
No.
If you wrote down a Hamiltonian.
No, I wrote the Hamiltonian without having a real cavity. This was, now we don't have a Hamiltonian description, but the theory that I presented you before of the QED DFT doesn't rely on the Hamiltonian description. It's more of a time dependent, and give you an equation of motion, which is a master equation of motion, and then you can couple with this description. However, now that you raise the question, there is one problem. This macroscopic QED is only valid in the dipole approximation. There is a problem to go beyond. The theory, the QED DFT that I told you is exact, works dipole, quadrupolar, all that. But the macroscopic QED, no, the way it's been implemented. How to go beyond that is an open question in theory. Okay, but we can discuss that later. For all that has been discussed so far, the dipole approximation is a good one. But I want to be critical with what I'm presenting. Okay, but anyhow, from now on, there is no cavity. My cavity are perfect mirrors, and I will have not modes which has no lifetime. Okay? And then basically what I wanted to show you is this idea of non-equilibrium, which was presented is Floquet versus cavity. And then there is a Floquet to cavity mapping that you can describe many of the properties in the Floquet system with a proper quantum environment for the matters part. Okay, let me just give you a highlight. I'm not going to show you the results, but this has been a work that I presented already in the past. STO is known that if you drive the system, this was done by Andrea and also Keith Nelson group, you drive the soft phonon mode, which is the TO mode, you can induce a paraelectric to ferroelectric transition. Depending on how you do it, the lifetime of this ferroelectric transition that you generate is longer or shorter. In the case of Keith Nelson, the ferroelectricity lives only while you are pumping, not much longer. However, the idea is that you have this strongly fluctuating dipole, which is the TO mode, that is the one that gives you the transition. Then the question is, what happens if you couple the cavity to that mode? Okay? And then the story is long, but then basically what I'm trying to tell you is exactly what Daniele presented. You have the temperature, and you have the light matter coupling, and you can have in the tetragonal phase or in the cubic phase, you can have a quantum paraelectric to ferroelectric transition as you increase the light matter coupling, as well as you can have quantum paraelectric to paraelectric if you increase the temperature. And then you can go to the cubic phase. This was the playground in which we started all the thing, but this is not what I wanted to show you. What I wanted to show you is all the results that are new based on the functional. And then let me just grasp with the 2D, then attack, and many people will discuss it later. Then there is a whole plethora of a family of 2D materials which are ideal to be incorporated in the cavity because they fit this Fabry-Perot structure, and then you can go from insulator, semiconductor, and even superconductor. You have niobium diselenite or magnesium diboride that I will show you in a minute. However, there is also something which is interesting. If you go look to the monolayer, the bilayer, or the bulk, the properties of the system change with the stacking sequence. And not only that, if you just rotate, you have another degree of freedom. No? I will not discuss the Moiré physics, which is this cavitronic, but I wanted to show you one case, which if you take a bulk tungsten ditelluride, which is this case, experimentally has been demonstrated that you can go from the vile semimetal to the trivial semimetal, which is a transition from the TD phase to the T prime phase. This has been monitored by ultrafast electron microscopy at Stanford, and this is a nice way in which you can really pump the system and keep it for long in the metastable 1T prime phase. Okay? The question is, can I do the same with the cavity? No? This is what I told you. This is a trivial exercise. If you just plug the numbers, the first thing I want to tell you is all these experiments with the density functional theory, we can predict the same results that they got with the light-driven phase. Then with the same theory, but now adding the cavity, what we get is the following. Is in the gas phase, you get basically what I showed you before. The ground state is the TD configuration, and the excited state is the 1T prime, then it's missing the T prime, sorry, which is a little bit high up in energy, which is only 4 millieV. Now, if you just do the same calculation as a function of the light matter coupling, what you can say is that for small light matter couplings, the stable configuration is the TD. However, when you reach 0.1, you get that the T prime is the most stable one. Then this automatically, what it's doing is that the system undergoes a shear mode. And this is eventually something that you could see. In this case, you go from bile to trivial metal. Then maybe it's not interesting, but if you were doing it in the monolayer, you will go from bile to topological insulator. And this is an automatic, and the only thing you need to have is the cavity resonance in the terahertz regime. And then we can discuss why. If you put it at high frequencies, it will not work. But then, the last part of the talk, I wanted to address something that you've been discussing, and is superconductivity. No? And then the superconductivity, there has been many proposals, including us and others. Also, Dieter is here in the audience. One is can I tune the cavity to modify the electron-phonon coupling? This is something that you've been discussing before. The fact that you have light-induced modification of magnetic properties coupling to phonons tells you that there is a magnetic phonon coupling that is modified by light. The same is if you ask for the electron-phonon coupling. I will try to get it done. Then this is the part I will show you now, how you do it with phonon polaritons. But then there are other proposals by modifying the interaction between electrons due to cavity modes, which is more of an electronic nature. Okay, let me first remind you what is magnesium diboride. First, this is the gap equation. You have two gaps. One is for the sigma and the pi sheet of the RUBIO zone. And then the TC is close to 40 Kelvin. It's 38, I think. And is the prototype of an electron-phonon mediated superconductor. At least on that, there is no doubt that electron-electron correlations do play a marginal role besides what you capture in the LDA level. Then this is good because the theory reproduces basically very well magnesium diboride outside the cavity. Also, we know exactly which are the phonon modes that do the nesting between the sheets of the two, which is the optical phonon modes. Then the question is, what happens if I put magnesium diboride in a cavity and I look as a function of the light matter coupling? Okay, the first thing is, which is something interesting, this is the structure, which is something which I wanted to tell you that you need to keep in mind. This physics comes because everything you put in a cavity, the structure changes when you have light matter coupling. There's a small modification, both in the lattice constant in plane as out of plane. And this, okay, you might think it's small, it's really small, at 0.1, but okay, these are arbitrary large coupling, then don't worry. This is already strong coupling regime, but you get this modification due to having the cavity coupled to the structure. Then something that is in agreement with some of the calculations that Giacomo Mazza has done for other insulators is, if you look to the electronic structure, basically you don't see major modifications. You can plot the electronic structure in and outside the cavity, and you have to see very carefully if you want to blow up what is changing at the Fermi surface. Then there is not a major change of the electronic structure. However, if you look to the phonons, and that's what I was telling you before, most of the phonons do not change, except the ones that are the optical, the infrared phonon modes, which are the E2G, the V1G, and the E1U. And those ones are dipolar active, and they change. You can compare here outside the cavity, inside the cavity, and then relaxed geometry by quite a lot. And that is the change that makes you the electron-phonon coupling being controlled. And then basically what happens, if you just plug it in this calculation of the superconducting gap equation, you have the solution, which is the black, which is the 40 Kelvin. You have the solution around 50 Kelvin when you put the cavity resonance with the E2G mode. And then if you were putting magnesium diboride perpendicular to the mirrors instead of parallel to the mirrors, you will get a reduction of the TC. Okay? For that, what we did is a bulk magnesium diboride. You have to have the cavity frequency has to be such that the skin depth of the mode is such that goes through all the material, then cannot be a bulk, has to be a thin film. Then we can discuss all details, but this is basically what I'm telling you. The two phonon modes, I tell you later what means. One is in the perpendicular direction, the other is in the in-plane. You get this automatic increase of the TC. And then you can see that there are two contributions. This is for the relaxed geometry, and this is taking the geometry of magnesium diboride outside. There is always an increase, and the increase is bigger when you do the relaxation of the molecule, or in this case, the solid in the cavity. Okay, and those is just to give you numbers, which is you can use at 10 terahertz, and then this gives you the estimation of the couplings, and then basically you will get in this regime in which the TC will change by a few Kelvin, either going up or down by having this coupling to the cavity mode. And I think this is quite remarkable because it's one of the first indications that eventually could be done. We are going to face the problem that Daniel was discussing about the temperature, because the temperature here is not included as a reservoir, it's included as part of the gap equation that we solved.
So this is like the cavity is in the ground state?
Yes.
Ground state.
It's ground state cavity, and then what you do is you get that in the Liesberg equation, and then you solve the gap equation, as you did in the previous cases for magnesium diboride. And if that's not good, that's a problem. But then it's done exactly the same as magnesium diboride outside the cavity. Okay, and with that I'm done. Then I just wanted to flash two things that we are doing with Martin, which is something which I think is very promising. You can control magnetism. You can go from antiferromagnetic to ferromagnetic in ruthenium trichloride. You cannot get the quantum spin liquid, but it's something which is interesting. This is basically in the empty cavity how you go from the zigzag order to the ferro, and it's automatic. It's very easy and it's analytic. And if you drive it, you can get it to higher magnetic orders. And then basically with that, I wanted to summarize that this new field of cavity and Floquet materials engineering, we have developed this framework, which is fast, because it's as costly as doing DFT, that allows you to study materials in cavities and predict the properties. Then the question now is to test how much of those predictions can be validated by experiments or not, as was in the past with LDA. We can get all observables, and also we can introduce the realistic cavities and dissipation in the system. And with that, then basically you can have both chemistry and materials treated on the same footing. And then the key point here is what, again, Daniel was mentioning, how we can control quantum fluctuations in the system. And the best way to control those quantum fluctuations is with another fluctuating system, which in this case would be in the STO, the fluctuating of the phonon mode. In the magnesium diboride is this sort of IR active modes that are fluctuating. In the case of water, if you put liquid water, is the infrared catastrophe is being modified by the cavity. We just got those results, and you will get modification of the optical activity of liquid water in cavity. Okay, and with that, this is all the people, including Martin here, and then I thank you for your attention. I'm sorry it took longer.